So hello everybody again. So we are continuing with the Cartesian tree that we ended with the last time. So let me start from the reminder what it is. So it's Cartesian tree, which is in other ways named Treap again. So we had two operations. We have operation split. Sorry, I'm a little bit forgot how to write it.
Sorry, is it on my problem, but the quality of the video is...
The quality of the video is not good?
Maybe it's only my problem, but I assume with pixels.
Oh, really?
It was okay, but now it is not.
Oh, that's strange. Check.
No, it's okay. Yeah, it's better.
Because for me, I'm looking at my screen and I see what's happening there. So that's kind of strange, though. I don't know. Let me try another marker. Probably it will be better. So if n is null, then we do nothing. We return pair of two nulls. This will not work. If n dot x is less than equal to x, then we say pair left right split n dot r by x. We say n dot r equal to left, and we return n and r. Else we lr split n dot l by x, n dot left equals to r, and return left n. So this is the split. Merge is kind of similar. Merge node L and R. If L equals to null, then return R. If R equals to null, then return left. And finally, if left dot y less than equal than r dot y, then L dot right equals to merge.
Sorry, is recording enabled or?
Yeah, recording is enabled.
I think that we should see an indicator, but I don't see.
Again, I'm recording as in the last time. I'm recording it using OBS.
Oh, I'm sorry. Thank you.
Merge left dot right r, return left, else r dot l equals to merge. To merge left and r dot l and return r. So this is the place where we stopped the last time. Okay, do you see it properly? Or
No.
No, it's really bad quality.
What's happening? Yeah, I mean, sometimes we see it in a good quality, but at the moment it is not.
That's super good.
No, it's okay.
Okay, I will try. I will leave the meeting. I will make somebody as their co-host, and I will end the meeting. Okay, I tried this time. Whether it works. Is it working properly or right now, or there are some issues?
It's okay.
Okay, I hope that it will be good for the rest of the time. I don't know, like I haven't changed anything from the last time, and like, it seems this is the problem with the Zoom rather than anything else. So I'm splitting the node, into two. So do you remember, like, this is exactly the place where we ended the last time. So are there any questions about that right now, or was it clear? Okay, so it seems it was clear. So now we are adding additional stuff on how to calculate the number of nodes in the subtree. So you want to split by x, and you want to transfer the number of nodes in their subtree. For that, in each node, we will store additional n dot count. So how to change it? How to change their code so it will calculate the count right now? So for that, whenever we change their node itself, which we are going to return, we just simply add here function recalc of n here. What recalc is going to do? Recalc x. Recalc x will simply set the count of the subtree. What is the count? So you can see that we are doing this recursively. So for example, when we are out of the split, then L and R already calculated the count properly. So L.count will be the number of elements in the left tree, R is the number of elements in the right tree. Then we changed N to R, so instead of N.L, we placed there L. And we want to recalculate their number of elements in N. So you ask recalc of N, and how to calculate their count inside the node. How to calculate the count in the subtree of X.
So are we stopping when we are we stopping the split and we will have a two subtrees, and after that we should count.
Sorry, don't follow.
Yeah, we do. Sorry for this. So first we will split and then we count.
No, I'm just telling that you have to add recalc here. So like you want at each point of time maintain the tree in such a manner that in each node you will maintain the total number of nodes in the subtree. Okay. So you can like why do we need this? That's a good question probably. So we have a query, for example. Please tell me the number of elements bigger than x. How you will answer this query?
Okay, if you have count, we can just count, because since it's tree, we found the place of x, we know that it's also in binary search tree order, so every left branch would be less.
No, I'm asking for the simple solution. Suppose you are given split and merge that already counts for you everything. How to simply solve this problem? You just split by x, you get two trees, and you ask the count of this subtree. Have L, R, and the answer will be R dot count. Is it clear? Is it clear, given the split and merge that maintain counts, we can simply count the number of elements that are bigger than x.
Okay, bigger. Now I understand this. What was in my case? I was like less. Why it's not left?
Okay, no, I wrote here, so I don't know. Probably it's bad quality, so it's number of elements bigger than x.
Okay, yes, that's good.
So the question is how to maintain their counters, like our count thing. So when we change the node, we simply, so the question, the quality is still bad?
No, quality is okay.
Quality is okay, good. So what should I add here? So when I change the node itself, I should recalculate the number of children in it. So what should I add here?
+1.
Okay, now you should add like recalc of L, and here you should add recalc of R. Because you change the left tree, and you have to recalculate. Right now you have this magic function that recalculates like the count in our tree. So we should call recalc of L because we changed the node L, and here we change the node R and call recalc R. Okay, so the question is, you know the left children, what it's here, for example, we know the left children of n and the right children of n, right? N dot left is n dot left and n dot r is L. Because we are working recursively, n dot L, so it was n dot L, n dot right, and n dot left hadn't changed at all, and n.r is already recalculated the number of elements in its subtree. So the question is, how to write a recalc function for a node, since we know both of its children already recalculated properly. So to what equal the number of elements in the tree of x, how to calculate it?
Given that we know that its children already calculated.
Yeah, we know that its children already calculated, because we call here recalc when we already recalculated in the previous split. So you here when you split, you know the number of elements in left and the number of elements in right. So it is simply l.count and r.count.
We sum up the number in left children and right children have.
And?
+1.
+1, yes. Yes, exactly. So it is the number of... So of course it will be a little bit complicated, because if xl equals to null, then we should return 0, otherwise we return xl.count. So we take the number of nodes in the left subtree, then you take 1, because this is the node which are ourselves, so x, plus x.r equals to null, otherwise it takes r.count. So this is how we recalculate the number of elements in the subtree. So that's how you can answer the question, who is there? How many numbers are bigger than x or less than x? Like, it doesn't matter. We just call split. We get the count in the corresponding tree, and then you merge it back. Okay? Are there any questions on how to calculate the subtree count of the subtree, like the number of elements in the subtree? Because this will be important for the further further algorithms. So now, then, if it's clear, then now consider a different problem. Which can be solved with the following name: Treap with hidden key. With hidden keys. Suppose you are given the following queries. Please take, so you have people standing in the row. I know that they are a little bit squarish, but like these are people. And they're kind of numbered from 1, 2, 3, etc., L, etc., R, etc., N. And you have a query, take front, the people from L to R. Or there is another, let me, sorry, like that's wrong thing to start, unfortunately. Take front, I think it should be further. So, and there is a question that each person has some number of coins. And the first question is, please tell me the sum of number of coins of the people from L to R. Okay?
Again, the sum of number of coins, like how many coins do people have from
Yeah.
all to R?
So you have people standing in a row from 1, 2, 3, etc. n, and there is a query: how many coins do people between L and R have? How many coins in there? So we kind of already did this, because if we maintain not their counts here in the previous algorithm, if we maintain not counts by this but the sum of values, something like that, we could, for example, ask like so you had a subtree, and for example you asked how many coins are there for elements bigger than x. Then you can simply store in n.sum, which can be recalculated as n.left.sum plus coins, x.coins, plus n.r.sum, and it will be exactly the same. So we put it in the recalc function, and it will calculate the number of coins per elements that are bigger than null. Now I will explain a little bit different thing. So we already know how to maintain their how to maintain their counts, like the number of elements in the subtree. So how would you like to answer on this question? You would like to split here, you will have 3 trees out of that. Then you take the thing that is stored here, the sum that is stored here, and it will be your answer. So if you know that all your persons are enumerated from 1 to n, their keys is corresponding number, and then to simply answer the query of sum of L and R, you simply split by L, split by R, and take the sum that is maintained in the root of their middle tree. Okay? So you just replace recalculate with this function where n.sum is recalculated from both of its children. And then when you want to transfer the sum of L to L and R, then you simply split by L and R and take the middle sum. Is it clear, or is this complicated already? If it's not clear, I would be happy to explain more, because it seems that like I'm explaining this topic. I'm feeling that I'm explaining this topic not very clear. So I would like to answer your questions.
I'm sorry, I'm talking for me, but I'm like completely lost, and I think the only solution that will work for me is to explore it after, because we spend too much time, and so yeah, and I'm still at the start, so yes, I do not just know what questions do I need to ask.
Everybody else feeling the same?
Well, kinda, but okay, maybe shall I explain how I've got it to understand if I've got it right? Like we have the subtree, and we collect, we store sums in there. So if we want to find the sum of the coins from L to R, we split and find the subtree that contains somehow coins from L to R, and their like top is their sum.
Yeah, so yeah, approximately. So yeah, I see that there is some. So
It's actually, to be honest, the question is not about like the sum itself, but about the tree, because I think like we go further, but I don't understand the main concept of the tree. I guess.
So
it's like,
for about the concept of the tree, you should understand that there are two functions only. There is split and merge. Okay?
yeah, I understand that.
This understand. So you can split by some value and you can merge two subtrees together. So how to get the people from L to R with two splits?
Split M to L and then R to. I'm not sure.
Yeah, you split by L. By L. And you get one tree that maintains 1 to L minus 1, so this will be one tree, and another tree that stores L R M. Then you want to calculate their the total number of coins of the people from L to R. You know that here at the top, you have this sum field that maintains their sum of the elements in its tree in general. So for example, here we have the sum at the top is the sum of their coins of first, second, etc. and the L minus 1. Here is the similar. So you have in the root, because we maintain this every time, in the root we have the sum of the elements from L to N. However, the question was not about their prefix or the suffix, but the question was for their L to R. And for that I asked, okay, how can I get their tree that contains only elements from L to R? Then I should make split here by R plus 1, and you will get the tree that maintains elements from L to R, and the tree that maintains elements from R plus 1 to N. And then, because how we build everything, we store at the root the total number of coins of all the people in its tree. So you store here, like if you take this subtree T, then T dot sum stores exactly what you want. And when to come back, you just merge here, merge to this tree again, and then you merge it here to tree back.
Yeah, okay.
Is it clear right now, or I lost you completely?
Well, at least this part is okay.
Okay, good. So, and how to maintain the sum? You just take split function, merge function, and where you update the node, you just recalculate their sum in the subtree. Okay. However, right now, we add additional query to our data structure. So right now, this query was only sum L and R, but we never changed the array at all. So this is kind of fixed data structure. You have people and you want to answer only from L to R. By the way, what is the complexity of this algorithm? Of one query?
The complexity of what is the operation?
Of one query, sum LR. What is the complexity of sum LR? Okay, let me
have this tree, or we shall build it.
No, you already have this tree. So you build the tree already, and you are asked several queries, like sum L1 R1, sum L2 R2, sum.
Basically, the amount, like the operation of split and the operation of merge, right?
Yeah. What is the complexity of split and the merge?
Should split work as local n?
Yeah, split and merge works in the height of the tree. Split and merge works as the height of the tree, and the height of the tree or Cartesian tree is of logarithm n. So split and merge work in of logarithm n, as Elizaveta said. So then, how this will work? What is the complexity of each of these query? Okay, it seems it's... Yeah, but like, remember the complexity, for complexity, their constant doesn't matter.
Okay.
So it is of logarithm n. Yeah, so the question was simple. So, okay, so let me then... I haven't taught this for a long time, so I thought the time I was ready to do that, but like my mind a little bit crumbled right now, so I want to understand what is the right way to explain things. And suppose right now that you have additional function as add to element I the value x. So you have two types of queries right now. You have, please answer me the sum, and please add to the ith element x. So we know how to maintain sum LR. It is simply we take split, we take the sum from the root, and this will be our sum. But how to add in this whole thing? How to add their value to the element? to some specified element I.
Like add a coin, you mean what?
Yeah, the number of you want to give their ith person X coins.
And coin is a key. Number.
I is is the identifier of the person from left to right. So you know that your persons are all identified with 1, 2, 3, 4, etc. m. And you want to give to the ith person X number of coins.
Shall we just find the ith person and add X coins and then go up and add X till we finish to the top?
Yeah, you can do that. That's true. But I would like to kind of write less amount of code and to work using split and merge. So remember that our rebuilding function is n.sum equals to n.left.sum plus x.coins plus n.r.sum. So, okay, let me try to give you, let us work together and understand how to do this. So, when we want to get sum from L to R, we make two splits and get exactly the proper tree that contains only elements from L to R. And here you want to operate on one element that is number I. What do you do in this case?
We split like I minus 1, I plus 1. Or...
Yeah, a little bit different. We split by I minus 1 and split by I.
Ah, okay.
Okay? Because if you split by I plus 1, then you will have I and I plus 1 in the tree. So here is ith person, here is I plus 1, and here is I minus 1. So if you split by I minus 1 and I plus 1 here, then you will have both of it in your tree. You don't want to have this, right? So you want to split it by I. Then what should you do? So you have this tree, which is, I don't know, for example, T. And you know that this T consists of only one node. And that's all. It is node exactly of ith element. So we have to change something. So we have count and we have sum. What should we do?
Change sum. And we want to change count.
However, you should change count also. That's... is it clear why we need this, or it is not clear why we need this? Because t count, the count of the node, is the total number of coins that person has. So if you add x coins to the person, then you simply increase it by x, the count. And then you should also change the sum. And since it is only one node, then we can write the sum like t sum equal to t dot count. And then you make two merges. So you make merge this with this and merge this with this. Simply back. So this is how you implement add. Okay, we're coming to much harder problem.
Please, 30 seconds just to understand. Just
okay, sure.
And the upper nodes, not the nodes, but upper like sums will be recalculated during the merge, right?
Yeah, because in merge you have here recalc function.
Yeah. Okay.
Okay. You have here recalc function, so it will be done automatically. Your merge and split always recalculates their everything.
Yeah, fine.
Okay, then we come to much harder problem. This is very important. The problem is that typically this topic is explained in 4 lectures, and I try to fit this into 2, so then you're a little bit, it's a little bit complicated. I understand. So you want to add x to all the elements between L and R.
Okay, first step would be split.
Yeah, you're doing it right. Yeah, you split by L, split by R, split by L minus 1 to be more precise. Split by L minus 1, split by R, and you have this middle tree. The problem here is that you get all the nodes that lie between L and R, right? The issue is that if you traverse all of them and increment them by x, then you will spend all of R minus L time. However, I want to do this in of logarithm n time.
Can we somehow play with sum, like on the top, like we producted it to x and then go down?
Yeah, but in this, yeah, this is exactly what we want to do. We want to tell that t dot sum plus equals, yeah. You also, except for sum, exactly here, you should also maintain the count that we talked previously. So the recalculate function will consist of 2 lines right now. So recalc will be, I will simply write recalc n dot sum and recalc n dot count. So if we know the count and the sum, then what we should add to t sum? You should add x times
Log n?
t count.
I'm sorry, I'm lost a little bit.
So you maintain the count. So when
Yeah.
you have to add how many x's? You have to add the number of x that are total the number of elements there.
Yeah, it's obvious.
So which is t count, and you multiply it by x. Okay, the problem is that you kinda don't want to traverse it in the future and add to all the elements in this subtree. For that, we made these updates lazily. So we had our node right now has sum, count, and now it will have a field add, which means how many I should add to the elements in this subtree. So you will say here t dot add. Sorry. So we will not do the sum thing. We just tell t add plus equals to x. Why it is plus equals? Because when we make, for example, we have two operations at the same time. We have add LRX and add LRY. So the first add LRX will take our subtree, which is L and R, and add an X to it. Then the next operation, it will add Y, and in total you will have T add equal to X plus Y. And you did this everything in constant time. Then, how to get, so for example, right now your tree looks something like that. You will have at each node, you will have some count and end this two. And you want, for example, to calculate the number of coins of the ith person. So you have this path. You have ith person here. So you know that it has i.count there. Oh, sorry, not count. We have coins also instead of. So we have third coins. So we have these coins here. And what is the total number of coins of ith element will be? Of ith person. You are passing through all this path, and in each moment you know that you have to add to the subtree this value, which is add. To add to all the elements. Then how to calculate the total number of coins of the ith person?
I would say that we shall extract, but I think I'm kind of lost.
The answer is pretty simple. You just go by this path, and you know that at each node you can have which tells us, please add some value to all the nodes in this subtree. By that, you just go by this path.
Maybe I don't understand what shall we add, because as a guide, like the top is the biggest, the top is the sum.
Yeah, but
we go down, and I think I'm lost.
Okay. So again, was it clear that we have add cure L and R, and we split their L, like their tree to L and R? Was it clear?
Kinda, yeah.
Then, instead of changing sum, I will take a special field add, which will tell how many we should add to this subtree. To each of its elements. So to get the number of coins by ith person, we sum all their add fields on the path to I. I think, yeah, let me try to finish my whole setup, and it probably will start looking more reasonable. So when you come to split,
I'm sorry. T add is again the number of
coins that
we shall give. Okay.
That we shall give to each person in this subtree.
Yeah. Okay.
Okay. So this is kind of lazily doing. So like we instead of going through all this subtree here and changing sums, I just tell, please add to all people in this subtree the value x. So instead of going through all the subtree, we just add this helping information that please add me to everybody here. Then at each time when we visit a node, we will do the following. We know that we will make the push function, push n. We will change n dot, and we apply this add operation. We kind of, when we visit the node, we kind of push this operation to its children. So you say n dot sum plus equal to n dot count times n dot add. So you know that you have to add to all the elements in the subtree, like this n dot add. And you multiply this by n dot count, because this will give you how many we should add to the sum. Then I tell n dot coins plus equals n dot add. Then I tell n dot l dot add plus equals then n dot add. So I kind of push to the left child. I wanted to add n dot add to all the guys in this subtree. Then I tell you should add to all the guys in the left subtree this, and you should add to all the guys in the right subtree. And since we already applied it, I tell n dot add equals to 0. So every time I visit the node, I kind of propagate the information about this huge operation in its children. So for that, I should add here push n, and here push left, push right. So I kind of tell their operation, please wait a little bit, I will get to you later. And when you have to go lower by the tree, you just propagate this information. So right now, when you want to, so yeah, please know that you don't have to change anything for n, because n dot add at this point is equals to 0. So you don't have to change add field here. Here is the same. The left field of the l dot add is 0 and r dot add is 0 here. So simply you split left, you split right now, and because of your pushes, you visited this node already, and it was propagated to the children. So in n dot sum, you will get their proper answer. I will give you a little bit of time to trying to understand what I wanted to tell you.
You're saying that we are not adding some number to all the nodes in subtree. We are just making a note in the field of a root of subtree that next time that we will go into this subtree, we should add a number that was specified in the field of the root of the subtree to the element.
Yeah, exactly. Exactly. So like here, I just go to this guy, I see that, oh, I have to add the n.add to everybody here. So I add it to the sum, I change the number of coins itself, and then I propagate this operation, kind of the operation that adds this amount, I propagate it to children. And finally, I tell that I have nothing to propagate afterwards.
Actually, I believe maybe for everyone is quite clear. It's just that Treap using split and merge recursively that make it harder. Because it's clear, and we make a note, and we will execute it later.
Okay. No, I want to understand, like, I want you to get the idea of how to do this in general. So that's how you perform like 3 operations. Sum, add to the element, and add to their subsequence of people. Now comes their more interesting operation. Now everything will become much more complicated. Not really much. Like from if you understood everything before, then it should be kind of clear. So right now, finally, we go to the Treap with hidden keys. And we want an operation, additional operation. Move to front, LR. So what it will be doing, the query is doing this thing. So it takes the people from L to R that are positioned at the position LR, and we should move it forward. So the new array will be kind of this R1, L minus 1, R plus 1, M. And they kind of renumerated. So the new identifiers will be 1, R minus L, R minus L plus 1, then, and etc. So like it's renumerated. So the next, so you don't have keys right now. So previously you had for each person you have its own key. You have a key, their identifier of this person, which was from 1 to n. Right now you don't have the keys. You just maintain the dynamic sequence from 1 to n. And you ask, please take me the current person that is located in their position L and the current person that is located in position R, and please move everybody from there to the front. And then obviously everything is renumerated because like these guys are becoming their start of the array. What we want to do? As usual, how you would like to proceed? You would like to split by L minus 1, split by R, take the string, so like kind of split this into 2 trees, and merge them together, but in strange order. 2, 1, 3. You want the middle will be the first, and then 1 and 3.
I'm sorry, why can't I just delete the tree, move the elements from L to R in the beginning and just build another tree?
How do you build another tree?
Like the tree, like, okay, we've got an array, right? It's not a tree itself,
Yes.
but we have an algorithm to make a tree.
Yes, but how, like, I will explain how to do this in logarithm time.
Okay.
The problem is that if you have keys, whole your data structure should support binary search key invariant. That everything on the left is less than in the middle and less than everything on the right. And when you just simply, like, we already told previously that merge works only on 2 trees, such that the keys on the left are less than the keys on the right. So you kind of cannot make merge straightforwardly. There. However, we can change split a little bit. So we want to split, take their, like, split to the kith element. Let us, like as previously, let us maintain in the node, like we have count in the node. So we maintain the total number of elements in the subtree. So consider our node and its children. And you want kind of split the tree in such a manner that the left subtree will have k elements and the right subtree will have n minus k elements. So how to do that when we know count?
We don't know what count is k.
Sorry?
Like we want to have k elements and we know that count, so we denote count as k.
You want to split the tree in such a manner that the left tree contains k elements only. Yes, and you have count. But right now you do not have the keys. You don't know about anything about keys right now. So how to change split function to work with counts and k? Okay, let me write. Probably it will be much simpler for you. So we take n.l.count plus 1. If it is less than equal than k, then I will ask n.l.count, oh sorry, k minus n.left.count minus 1. And here I will just ask for k. So that's it. We want to split our tree so that the left tree contains exactly k elements. For that I ask, how many keys do I have in the root and the left subtree? If it is less than key, then you have whole left subtree in the left tree. And then we should split the rest of the part to k minus how many we have in the left subtree. Or vice versa, if we have small number of total number of keys to the left, a higher number of the total number of keys to the left. Then you go recursively to the left child and split exactly k guys out of there. So this recursively will return that left will contain exactly k keys and R will contain the rest of the keys. That's all. Merge doesn't change. So, and right now, instead of asking, please split me by the left key and by the right key, you can ask, please split me at position L and please split me at position R. But please be careful here, because if you have this tree and you split at first, like if you split at first by R, then you will have two subtrees that this has R elements, and then you split by L, you will have exactly what you wanted to. So here are elements, but if you make it vice versa, so you split by L here at first, L, then you have to split the right tree to R. You cannot split it by R itself, you have to split it by R minus L already, because you want to have R items to the left of this split position. So this is very important to do this in the right order. So if you want to be everything to be more clear, then you should like at first split by the right and then split by the left. And then you can simply merge, and merge doesn't change anything. So for example, you have like very strange data structure that, for example, can add X to the elements between L and R currently and move some of the elements to the front. That's very interesting data structure. So this is the whole code that does this. Okay. Then let us talk a little bit about another operation. So like you can add and you can, for example, set the value. So instead of add, we could make set LRX. This will, everything of this will be different only in the push function. So for example, when we have set, so you have count, sum, coins, and set. How to write push function? So you have set is that this string, everything in it should be set to this element. How would you push it? So we already had push for add operation, but how to do push for the set operation?
Why should different from add?
In add we add this value, right?
Why that should be different, like?
It shouldn't be anything very different. No, that's true. It shouldn't be very different. So what should it? So and dot sum. what n dot sum is equal to?
And we are setting to sum.
Yeah, we are setting to like we make the set. Please make all the people on the from L to R to have exactly X coins. So it's not add, it's like we set all of them to have X coins. So right now, when you make push, you know that everything in the subtree has exactly X coins. To be more precise, exactly set coins. So what will be equal to the sum to? So you have count and set.
And count is okay. Sum is a sum of one person have, and count that everyone have in this.
Yeah. So it is n count times n dot set. Okay.
Okay. So
Each person, there are n dot count persons in the subtree, and each right now has set. Okay?
Yeah.
Then, what should I do with coins? How many coins this guy will have?
Set coins.
Yeah, set coins, right? Set coins. Then, what we should do with with child, with the left child?
It's also equals to set coin, but we should just remark that next time with
It should be n dot set. It's simply the set operation simply overrides other operations.
Okay.
That's clear? Why? Suppose that you previously in the left child if you had in the left child another set. The problem is that our operation was later, and it will make all the elements in this subtree to be X, or to be set. Then you just simply set here. So you have n.r.set equals to n.set, and then you tell n.set equals to some bizarre value, I don't know, infinity. And for example, here you should set if n set equals to infinity, then return. Then please do nothing. So this is how set. And consider another very interesting operation. I will move set. And we have an operation reverse. So you want to reverse everything between L and R. So you kind of want to take. So here is the array from L to R, and you want to make from this an array R left. So you reverse the whole subsequence. We just reverse it here. Again, as with the sum and the add, reverse operation is very good to this push operation, because when you take the segment that you reverse once and then you reverse twice, the operation gets to the same condition, like not the operation, the array gets to the same state as previously. So instead of set, we will tell reverse, which will be a boolean value that tells you should we reverse this whole subtree or not. Then how push operation should be performed. So So consider our tree. We want to reverse it. We want to reverse all the values here. So it appears that, like this tree, so this tree reverse will be as this value, but with R reverse and left reverse. So the reverse of the tree is kind of also recursive operation. We should we should replace two children, and we should reverse them itself recursively. Is it clear why?
No, it's not clear.
It's not clear? Okay. So, how it looks? So we have L here, X here, and R here. How will reverse of this thing will look like? Of this segment? This element goes in the first, like when we reverse, this element goes into the first position, this second element goes to the second, and etc. until here. Then we will have X here. And everything from the left is coming like afterwards. Please see that you can see that this R is R reversing, because you just take the latest element and put it the first, then the second to latest element you put it the second, and etc. So you kind of reversed the string L, R, and the same happens here.
But as it is like this, if we are using the sequential array, but when we storing trees, we are using these positions like in 2 in 3 plus 1, so we just can take it and reverse them as a part of this array.
Can you repeat? Sorry.
So if we demonstrate reverse as a part of array, taking part of array and swapping its front with its back, when it's reverse in this, but when we are storing tree in the array or list, we are using indices is their position, and they are not concentrated ever on left part, on the right part. So when we just trying to swap lefts of tree and rights of tree, it's not just swapping them.
No, consider you can. No, it's not just swapping. It's kind of so. Let us. So this tree, if you write it from left to right, it is something like that, right?
Something.
So it is exactly, to be honest, it's exactly like that, because like this guy stores everything from 1, I don't know, to n. So you know that each element has its own position. So like it is exactly 1 to n here. So the ith element in this tree is the same as the ith position here. So this is exactly mapping from this trip with hidden keys to their array.
So it's mapping.
Yeah.
But mapping, so yeah, but then we lost clear.
Yeah. So and then you can make a reverse similarly for the tree. Like kind of, you can think of this tree as the array, and the array is the tree because you maintain for each element you maintain its position in the array. So
I just started to talk about arrays because I was thinking
how to perform arrays?
No. Swapping, not in arrays, but in trees.
Okay. In the trees, you can see that it is kind of like to reverse a tree, like it's the same as to reverse array, kind of. You just have X in the, so like here in the array, you can see that the reverse of the array is like right reverse, X left reverse. So if you map kind of back to the tree, you will have X and everything on the left reversed tree, and everything on the right, on the left becomes right that is reversed. So you simply have to swap two children and tell, like, please reverse itself.
And by swap, you mean its children.
Yeah. So like let me write push, and probably it will be a little bit better. This desk is no good. So our push operation, push X, will now tell the following. So if X dot reverse, if we want to reverse this subtree, then you have to change its children. So you have to change LR. I will read from x.l, x.r, and I will tell x.l equals to r, x.right equals to left. Then I tell, okay, please reverse it in the future. Not x.reverse. X.l.reverse. X.r.reverse equals to not x.r.reverse. And then finally we tell like x reverse to false. So what I'm doing here, so when I see that our subtree should be reversed, I tell, please swap my children. Here I swap two children's. And then you should propagate the reverse to its children. So tell that the left guy should be reversed and the right guy should be reversed. Obviously, unfortunately, not obviously for you, I think, but like it should be x.l.reverse equals to not x.l.reverse. Because it was it could be reversed before. So, and the reverse before, if we reverse the reverse, we will get the proper sequence. So you just stay here, not x.l.reverse, and then you finally tell, okay, I reversed the whole subtree and I'm fine with it. Did it become clear?
Why do you need both x reverse and x right? Okay.
Yeah, because you reversed both of its inside.
Yes, right. I just wrote it for the dot between L and reverse. Okay, it's black. Just Fine.
Okay. Is somebody has questions? Does somebody has questions further about this?
No.
Okay. I hope you didn't get totally lost. If you didn't understand anything, you can simply watch the wiki page as I sent you the last time, or I wrote it, I don't remember. So it was like what?
We have it.
You have it. Okay, good. So this is a good place to see if you didn't understand something. It contains not everything that I explained you today, but like it should give you the intuition on what did we do today. Okay, so that's all. Thank you very much for coming.
Thank you.
The next time will be, I don't know exactly in which manner, but next time we will not have the lecture, and you can ask me questions. Like, I think we will maintain this in Russian the next time, so it will be easier for everybody. So you can.
I mean, we will not have a lecture. Like,
what? Sorry.
you said we won't have a lecture next time?
Yeah, we won't have a lecture next time, but we will have like question answer session or something like that.
Oh, okay.
Okay? This will help. Also, this will help you to get in touch with the problems that there are already a lot of them to solve. So,
Thank you.
see you. Thanks. Bye.
Goodbye.